Welcome to a lesson with Dr. Powell. Let's take a look at transformations of the unit hyperbola. So a unit hyperbola, in contrast to a unit circle, is not inside a box like an ellipse is, it's outside the box. So here's an example. This circle on the inside has equation x squared plus y squared is equal to 1. That's why it's called a unit circle, because it has a radius of 1. Square root 1, you get 1. And this box goes out 1 this way, 1 that way, 1 this way, and 1 that way. Now we put diagonals through the box, and we go from this point this way, that way, and we reverse and do it over here. This is an example of a unit hyperbola, where its equation, instead of x squared plus y squared is 1, is x squared minus y squared is 1. Now there is another unit hyperbola, so there's actually two, centered at the origin. Again, we have the same box that has the unit circle in it of radius 1. Then draw diagonals. And then from this point, we just go up that way, and we reverse down here. So this is another unit hyperbola. Let's call this, this is actually negative x squared plus y squared is equal to 1. Now, you can kind of see a few things. First of all, in this particular case, notice that when x is 0 and it's not there, you'd end up getting negative y squared is equal to 1, which is like y is equal to I plus or minus. And we don't want that showing up. So notice that there's no graph at x equals 0 here. And you also have the same thing. If you set y is 0 here, there's no graph because you get something complex. So whichever one of these x squared or y squared gets the positive rules out in telling which way it's opening. So over here, notice how the y squared portion is positive, so it's opening up and down. Over here, notice how the x squared portion is positive. That means you open to this side and that side, so side to side. But pretty much, if you know how to transform this unit circle equation to an ellipse, that ellipse has a box. Well, guess what? That box is shared by two hyperbolas, one this way or one that way. So really the same basic ideas hold. You're still going for the same box, but instead of drawing in the box, you draw outside the box. Here's an example. What if we had something like x squared over 9 minus y squared over 4? Okay, and that's equal to 1. Well, if this were an ellipse, so you would have a plus if it were an ellipse, then what we would have is we'd have centered at the origin, notice, and we would be going in the x direction, 3 in the both ways, and in the y direction we'd be going up 2, square rooting 4 and square rooting 9. So this tells us the box for the ellipse if this was a plus, but since it's a minus, we draw something on the outside. Now, which way do we open? In this case, notice how the x squared part is positive, so we open up that way. And we have just drawn this hyperbola. Now, let's look at another example. Suppose we have negative x plus 1 squared all over 25 plus y squared is equal to 1. Okay, let's look at this. First of all, notice this is like y squared over 1. So our box in the y direction is going to be going up and down 1. In the x direction, it's going to be going side to side 5. Now, where's the center? The center is at -1 and 0. So -1, 0 is the center of the box. Keep that in mind. So this point refers to the center, -1, 0. And let's go outside to side 5 and up and down 1. And that's our box. So our hyperbola will be drawn on the outside of the box. Draw some diagonals here. Now, does it open up and down or right or left? Notice the y squared wins because it has a positive here. So therefore it opens up and down. So it starts from right here on the center of this edge right here, the box. It just goes right here to there. On the other side, from here to here, where these diagonal lines are asymptotes. And the neat thing about those asymptotes are that they're just transformations of what they are, of what the other ones are, just like everything else is hyperbole, ellipse inside the box, everything else, even the lines are transformations that follow the same transformations that you see here for x and y. In fact, if we wanted to, we could actually write out, this looks like x plus 1 over 5 quantity squared. I think 5 squared is 25. And this is just plus, it's a negative plus y squared. So really there's no transformations in y, but there are transformations in x in this particular case. So originally, we have that the asymptote lines are at y equals x and y equals negative x. If we were thinking about a unit hyperbola, so with a box of 1, 1, and we're just doing a transformation of these. Notice that in this particular case, so we could basically just do our replacements. Notice how x is replaced with this. So we could say y is equal to x plus 1 over 5. Hey, that's the equation of one of these lines. And guess the one with positive slope even. And the other one has the equation. We'll just take this one and replace x with what it is. It's y equals negative x plus 1 over 5. Of course, in this particular case, we didn't have to replace y with anything, so that was nice. But still, we can come up with the equation, with the graph of the hyperbola, and even know what the equations of the asymptotes are, just by doing the same type of transformations that we were doing with ellipses. Finding the box, we just draw on the outside, and we need to check, are we opening up or down? To find the equations of the asymptotes, you just basically write these in terms of squares, and pretty much it's just whatever's in here equaling what's in there. And also what's in here equaling negative of what's in there, just like we have here and here. We'll work through some more examples of that. Thanks for watching.